join. Good evening. Welcome you all for this lecture 3, Professor SVM Satyanarayana online memory lecture series. I welcome Dr. our today's resource person, Dr. Mohammad Sajjad, Professor, Department of Physics, Aligarh Muslim University. We are so thankful, Professor, for accepting our request immediately. So, this program is intended to organize, to disseminate, and also share the Professor Satyanarayana's legacy and life and his contribution to physics. Last year, untimely, he passed away due to health reasons. So we don't want to stop his passion. So we started this lecture series in the month of January. The first lecture given by Professor Athar, and the second lecture is given by some other professor. And this is the third lecture, and I really thankful to our today's resource person. Without waiting the further time, so I invite one of our Sunday class students, Dr. Mridalini, is also our Satyanarayana student. She is about to submit her thesis, so she will give us some kind of a short introduction about this program. Mridalini.
Thank you so much, sir. Can you hear me?
Yes.
Okay. Good evening, everyone. I would like to present my heartfelt gratitude to the organizers for giving me this opportunity to present an overview of Sunday physics classes and the memorial lecture series in honor of our beloved professor, Professor SVM Satyanarayana. Many of you may likely be familiar with the Sunday physics classes, but for those who are new, I would like to share a brief overview. The Sunday physics class was an extraordinary educational initiative led by Professor Satyanarayana. We call him affectionately Satya sir. Satya sir is a distinguished physics professor at Pondicherry University and began these classes in 1996 while he was pursuing his PhD at IGCAR Kalpakkam. The primary aim of these classes was to help postgraduate physics students to prepare for competitive exams like CSIR NET, GATE, and JEST, which are crucial for pursuing PhD at India's premier research institutes. Every Sunday from 10 a.m. to 5 p.m., Sunday classes were held at the Department of Nuclear Physics, Madras University, and these classes was free of charge. Despite the deep learning that we have got from Satya sir, what made Satya sir's classes so unique was its approach. Rather than just simply completing the subjects for the sake of syllabus completion or anything, the classes emphasize on the deep understanding of the concepts, to develop a feel for the subject and its real-world applications. In fact, we also had many sessions where many experimentalists would come and perform experiments for us. It has fostered development of our problem-solving skills, and also we have developed as a community of passionate learners who are profoundly inspired by our mentor. Satya sir conducted these classes with unwavering dedication for over 25 years up till his health began to decline in 2021 due to pancreatic cancer. The class became more than just a learning opportunity, and it has transformed many of our lives. Many of the students have gone to become researchers, scientists, professors, and prestigious institutions across the country. To continue Satya sir's legacy and his passion for teaching, the students of his Sunday class have initiated a periodical memorial lecture in his name. This lecture series will cover topics in undergraduate and postgraduate level physics subjects and experimental subjects, as well as the education and teaching. Like many students who have benefited from these classes, including myself, we are committed to carrying forward Satya sir's dream to make physics and learning more enjoyable and accessible to all students across the globe. Thank you.
Thank you, Mridalini. Now I invite Dr. Tirusandil to play a short biography of Professor Satyanarayana.
Thank you, Joseph. So I'm playing a video on the memory of Satya sir.
But if it is satisfying only 1, 2, and 3, then that is called a monoid. These are just names for they exist, so I am right. And if it satisfies 1, 2, 3, and 4, it's called a group. And if you may want to call it as a 5, if it satisfies 1, 2, 3, 4, and 5, it's called an abelian group. Learning science is not about answering a question, but it is a training to question the answers. I believe that we must judge the progress of a student not on the basis of answers that he writes in the examination, but only on the basis of questions that he asks in the class. Because the ability of questioning gives us a window to judge the understanding ability of the student. So I think, in my opinion, the first and important aspect of teaching is to make them ask questions. Now, this is a very, very tough task. We have a group of heterogeneous people with different backgrounds, different knowledge initial states, and we cannot easily make everyone to come out in open and ask questions. There will be a lot of inhibitions, there will be fear, there will be a doubt that others will ridicule, all these problems will be there. But we have to deal with all of them, we have to live with all of them, and yet make some progress in terms of training them to ask questions. This is the only way to really judge whether someone is making a progress or not. Second important thing is how best you teach does not depend on you alone. It depends on you as well as the given set of students. So your teaching should be a function of the group who is attending. Suppose I learned group theory. I teach everywhere in the same fashion, but the audience in one place may be different from the audience in another place. So your teaching, the content, the method of presenting, and the problems that you choose, the way you present it, everything has to be a function of the set of students or the audience whom you are addressing. So if the audience are ready to receive, then only they will receive. How much ever clear presentation that you make, if the audience have no readiness, then it all goes waste. Now, purpose, what we have to do is you have to do an initial exercise of making the audience ready for what you have to teach. Okay, so how to make audience ready is another technical aspect which we will discuss. So you have to have a readiness. If you are not ready to receive, you will not receive.
Thank you, Senthil. So I invite you to give an introduction about today's Dr. Mohammad Sajjad.
Thank you, Joseph. I hope you can see the screen.
Yes, yeah, it's visible.
Thank you. So it is my honor and extremely honor to pleasure to have Professor Mohammad Sajjad Athar on behalf of Sunday class. I welcome via this short presentation. Professor Sajjad Athar is globally well-known physicist, and he is a chairperson and professor at the Department of Physics, Aligarh Muslim University in Uttar Pradesh. He is working in a broad research areas of nuclear and particle physics, where the particle physics experiments requires a deep knowledge about the interaction of neutrinos with the nuclear materials. So that is where the Sajjad sir is coming into the play. And these are all very important milestones. So he made it throughout his research. And Sajjad sir is almost nearly having 30 years of teaching experience. And I want to mention what he has done as a chair professor and professor. And he made this physics department of Aligarh Muslim University as one of the best place to study particle physics in India. You can check out the curriculum of BSc and MSc physics at that university, and it is extremely good, and it is incomparable with any other institute in the country. And other than that, I want to mention how Sajjad sir came to this position. He did all his degrees through Aligarh Muslim University, and he graduated in nuclear physics PhD. And he started working as an assistant professor, and he presently as a chair professor at Aligarh Muslim University itself. Along with that, he is having a visiting position across the world in Spain, Tokyo, in Japan. So, if you want to talk about Sajjad sir research, it cannot be counted with the numbers. I mean, he is so beyond quantifying with any of the metrics that we have. His research work is calculation of this atmospheric neutrino flux and how they are useful to the neutrino interaction with the detector materials is actually setting up the ground floor for any other physicist to play around. So it is like a foundation for any of the neutrino physics to happen across different experiments. So I am highlighting some of his research collaborations. One is in the Minerva and the another one is the deep underground neutrino experiment DUNE. Both are under the Fermi Lab in United States of America. Other than that, he is also a member of the Institute de Física Corpuscular in Spain, and also he is in the University of Tokyo Institute of Cosmic Ray Research in Japan. That institute belongs to the discovery of neutrino oscillation, and which led to the Nobel Prize in Physics. And also he is a member of, he actually collaborating with the Department of Physics in University of Canada, Spain, and he is an active member of India-based Neutrino Observatory. So to highlight how he is important in this research collaboration, he is working for a very long time with Professor Takaki Kajita. He is a Nobel Prize winner in the 2015, and he is a close friend of him, along with Honda, who recently passed away during Corona. Together, they calculated neutrino flux for the different experiments across the globes. For IMO site, they have calculated the atmospheric neutrino flux. Likewise, the group is actively involved in calculating the neutrino flux across the globe, which is for the fundamental fundamental stone for building and doing the neutrino physics research. And I want to mention what are the honors he have. That will take a long time to complete everything. I am only highlighting it here, what he is actually, how important he is and how he is well recognized in the globe. The first one is the NuSTEC, Neutrino Scattering Theory Experimental Collaboration. It is comprises of only 30 to 35, I think it is 33 members of a well-renowned physicists across the world. And Sajjad sir is one of the member, and he is like a living legend in theoretical physics. And this collaboration is a theoretical experimental joint initiative, and from India he is the only member. And also he is the member of Neutrino Panel of International Union of Pure and Applied Physics. Again, he is the only member from India on this thing. And he is also a member of European the particle physics research communities, and also member of various collaborations across the world. In my opinion, Sajjad sir spread his wing all around the globe, and he is well recognized by the global community as well as in India. And to highlight some more of his research activities, he used to be invited to provide summary talks in the seminars, and invited to provide lectures in the different schools. And also he is the editor of several journals and highly reputed journals. And along that, I want to highlight his author of review articles. So the review articles used to be written by global expert in the field. Recently, he's written on aspects of neutrino physics, and he covering the present and the future of neutrino physics in this review articles. It is the highest honor which will be given to any physicist to summarize that entire field, because Sajjad sir is one of the person who is having the thorough knowledge of this neutrino and particle physics. Now, although I can go about a lot of honors, for time being, I am completing with Sajjad sir's research contribution to the students. He wrote a book, The Physics of Neutrino Interaction. It is a very long book and completely covering all the areas of neutrino physics in the phenomenological, starting with the theoretical physics, and he is covering up to the experimental perspective of this neutrino physics. And it is a very big book, you can read it and you can enjoy. Recently, he is giving a particle physics course in SVM, NPTEL kind of thing, initiated by the government. And you can see there are more than 400 students are participating in this. With all these comments, I would like to welcome Sajjad sir to give this memorial lecture on behalf of Professor Satyanarayana's memory. Before finishing, I want to highlight several facts which is common between Satya sir and Sajjad sir. Whenever you find Satya sir, you always found him outside the class with the students in the tea or lunch any times. Sajjad sir is same and he is so friendly and very easily approachable to the students, and he helped students. And from the students of Sajjad sir, we come to know that whenever he is giving a public talk in that Aligarh, the auditorium will be completely filled. So I think these kind of similarities are there between Satya sir and Sajjad sir. Both are humble and loved by the students. So now I'm giving the stage to Sajjad sir to present his talk.
Thank you very much for the introduction. I don't deserve so much of praise, but it's a great honor for me to give a lecture in honor of such a great person, Professor Satyanarayana. I am going to stick to the basics, and I am going to use tab. I don't know the background of the students. Therefore, I will start from very fundamental things, and then gradually I will build up and try to complete the lecture, though it will be difficult. But if you wish, we can have many more lectures on this topic. And if you want to interact and learn more about the particle physics, I am always there. We can fix our time. And I will request you, Senthil, to share the screen, because I am going to use tab. Am I audible?
Yes, sir. You are
Yes, sir.
now, so we can able to share, sir. No issue.
Yes, sir.
Please.
Are you able to share? Yeah. Yes. I think it's started screen. Yeah.
Yes. Hey, 1 second, please.
It is visible, sir.
Yeah. Screen. Are you able to see the white screen, whiteboard?
Yes, sir, we can see it.
Okay. I'm going to talk about conservation laws in particle physics. But before I start talking about conservation laws, let me just talk about particle classification. We know that in nature we have different particles like electron, proton, neutron, neutrino, lambda particle, sigma particle, pions, kaons, but all of them are not of the same kind. They are broadly divided into. Senthil, I am disabled perhaps. They are divided into two groups. One is what we call by the name fermions. And the other we call by the name bosons. What are fermions? Fermions are those particles which obey Fermi-Dirac statistics. Fermions obey Fermi-Dirac statistics. All these particles have got a spin which is half odd integer multiple of H cross, means n is 1, 3, 5, etc. Like electron's spin is half H cross, proton spin is half H cross, but spin of delta is 3 by 2 H cross. Okay. Similarly, you have higher resonances where the spins are 5 by 2 H cross or 7 by 2 H cross. Therefore, you have particles which are called fermions, whose spins are half odd integer multiple of H cross. Then they obey Pauli's exclusion principle. That means you cannot put two identical fermions in the same state. Generally, in chemistry book, it is written that no two identical electrons, but it is in general true for two identical fermions, whether they are two positrons or two protons or two electrons, and then their wave functions are antisymmetric in nature. Therefore, these are the fermions. What are the bosons? Bosons are the particles which obey Bose-Einstein statistics. Yes, please. Hello?
Yeah, we can hear you. Please go ahead.
Okay.
Sir,
Bose-Einstein. Yes.
sorry to interrupt, sir, your whiteboard is not clearly visible. It is showing connection error. Is it only for me? I don't know. But
Yeah, we are seeing okay. It's okay. It's okay for us. Dipanjan,
Okay.
it's okay for
No,
us.
we are able to see the whiteboard. You can
Yeah.
try just reconnect.
Professor Sajjad, you can continue. Yeah, please.
Okay. Bose-Einstein statistics. Then here the spins are integer multiple of H cross. This n can be 0, 1, 2, 3. Like pions are spinless particles. Kaons, they are spinless particles. But you have rho meson or omega meson, etc., which are spin one particle. So therefore, you have particles which have got integer multiple of integer multiple of H cross. They do not obey Pauli's exclusion principle. Therefore, they do not obey Pauli's exclusion principle, and their wave functions are symmetric in nature. Therefore, we have to first understand that there are fermions and there are bosons, and once. And fermions are like electrons, protons. One second, please. It's not erasing. Then when we talk about these electrons, electrons, protons, or neutrons, or lambda, or sigma, these are all fermions. And pion, pi plus, pi 0, pi minus, or kaons, k plus, k 0, etc. These are bosons. Okay. But when we talk about these fermions are further classified into two groups. One is known as what we call by the name leptons, and the other what we call by the name baryons. Therefore, we have leptons and the baryons. What are the leptons? For example, electron is a lepton, and its accompanying neutrino, which we call by the name electron type neutrino, is a lepton. Muon is a lepton, and then a neutrino associated with it. And tauon is also a lepton, and a neutrino that is associated with it. This is called, we generally call first family, second family, and third family, because in the standard model of particle physics, electron lepton number is independently conserved. Similarly, muon lepton number is independently conserved, and tauon lepton number is independently conserved. And we write something like it. This is +1 for first generation of leptons. Similarly, for muon, we write it as +1 for the second generation of leptons. And for the third generation of leptons, we write L tau is equal to +1. And then we know that the antiparticle of electron is positron, antiparticle of neutrino is antineutrino. Therefore, if I write E plus nu E bar, mu plus nu mu bar, and tau plus for tau minus antiparticle, we have nu tau bar. Therefore, we have antiparticles for the first generation, antiparticle for the second generation, and antiparticle for the third generation. And this antiparticle has a lepton number Le is equal to -1. Similarly, here the muon lepton number is -1, and the tauon lepton number is -1. Therefore, for particles, the lepton number is +1, and for antiparticles, the lepton number is -1. But it is, if I ask you the question that I am talking about a muon, and what is the electron lepton number for the muon, the answer is 0. If I am talking about nu tau bar, and if I am asking the question that what is the lepton number for tauon lepton number for nu tau bar, the answer is -1. But what is the muon lepton number or electron lepton number for the nu tau bar, the answer is 0. Therefore, you assign lepton numbers to individually to the first generation, second generation, and third generation leptons, and with a minus sign to the antiparticles. And therefore, you have the first, second, third generation of leptons, and corresponding to that, these three generation of Then, if we talk about baryons, then we have proton, neutron, etc. as the baryons. And in the case of baryons, we have the baryon number. But in this case, baryon number is +1 for whether I am talking about proton, whether I am talking about neutron, or a lambda, or a sigma plus, or sigma 0, or sigma minus, or cascade 0, cascade minus, whatever particle you call, if that is a particle and a member of the baryon family, the baryon number will be +1. While for antiproton, anti-neutron, anti-lambda, anti-sigma plus, anti-sigma 0 bar, anti-sigma minus bar, etc. I am putting the bar. The baryon number is -1. Therefore, it is +1 for the particles and -1 for the antiparticles. Now, when I talk about sigma plus bar, then this means that this is a guy whose charge is -1, because when we talk about the antiparticle, the charge gets reversed. Not only the baryon number, but its charge also gets reversed. Next, we will talk about the other quantum numbers, but we have to be very clear that when I am putting a bar, we have to change the charge, and charge in this case will be -1. Therefore, you have particles like sigma plus, whose charge is +1 here, whose antiparticle is sigma plus bar, whose charge is -1. While similarly here, if we talk about sigma minus, then its antiparticle is sigma minus bar, and the charge of this particle is +1, while baryon number for this particle is -1. Therefore, you have leptons and you have baryons, but in the case of leptons, you have independent generation of the lepton families, and for that you assign lepton number individually to electron family, muon family, and tauon family. But in the case of baryons, you have common number, and that you call it as baryon number, +1 for the particles and -1 for the antiparticles. Now, when we talk about the quantum numbers, which I am calling it by exact conservation laws and approximate conservation laws, then what are the exact conservation laws? There are 4 conservation laws which have been given by nature, and then there are 3 additional conservation laws in the category of exact conservation law. Those are lepton number, baryon number, and CPT, which stands for charge conjugation, parity, and time reversal, all 3 taken together. Therefore, you have conservation laws. Somebody else also is writing, or it is because I am speaking and it is getting written? When I am talking about conservation laws, then there are 2 types of conservation laws: exact conservation laws and approximate conservation laws. What are exact conservation law? Those which have been taught to us in class 9th and 10th, that total energy has to be conserved. Here also you talk about any process, the total energy will be conserved. Then the second is the charge. Third is linear momentum. Fourth is angular momentum. See here, this angular momentum stands for the total angular momentum, that consists of the sum of orbital angular momentum as well as the spin angular momentum. Okay. Therefore, these 4 have been given by nature. But in the standard model of particle physics, we have 3 additional conservation laws, which we call by the name lepton number conservation, baryon number conservation, and 7th is what we call by the name CPT, charge conjugation, parity, and time reversal, or 3 taken together. Therefore, this stands for charge conjugation, parity, and time reversal. And the consequence of CPT conservation is that mass of the particle will be equal to the mass of antiparticle. The lifetime of the particle will be equal to the lifetime of the antiparticle. Magnitude of the magnetic moment of the particle will be the same as the magnitude of the magnetic moment of the antiparticle. Therefore, these 3 are from the standard model of particle physics. That means we have put it by hand. If someday it turns out that lepton number is not conserved, then that means we have to extend this standard model. That means if this standard model is really not a standard, that is why in the literature what we call by the name beyond the standard model. Okay. For example, there is a phenomena which we call by the name neutrino-less double beta decay. While when we talk about beta decay in a nucleus, what happens? Either a neutron gets converted into a proton, or a proton gets converted into a neutron inside the nucleus. And for example, I am talking about a daughter nucleus plus a positron plus a neutrino. Now, this is the conventional beta decay. But what people are talking about is a nucleus that is decaying into a daughter nucleus, and two positrons, for example, are getting emitted without any emission of neutrinos. And these are known as neutrino-less double beta decay. And some fine morning, if we read a newspaper that neutrino-less double beta decay have been found out, then that does not mean that something very strange is going to happen. Just it is because that our standard model is not sufficient to accommodate everything. But today, whatever we will talk about will be within the standard model of particle physics, and we shall assume that these three are the members of exact conservation laws. Therefore, we have 7 exact conservation laws, and I will take example of one by one to tell you that what are these: energy, charge conservation, linear momentum, and angular momentum. These are very basic things. For example, if I ask you the question that A plus B, these A and B are particles, and they are giving you 1 plus 2 plus 3 plus 4. For example, if I am writing a reaction electron plus proton, in the final state, you are getting electron plus neutron plus pi plus pi 0. These are 4 particles in the final state. Initially, you had electron and proton only. Then what is happening? This I am writing it as A plus B going to 1 plus 2 plus 3 plus 4. Therefore, the energy conservation will tell you that EA plus EB, that will be equal to sum over I 1 to 4 EI. That is all. For example, if a pion is decaying at rest into a muon and antineutrino, since this is decay at rest, therefore the momentum of the pion is 3 momentum of the pion is 0. And what is its energy? Its energy is nothing but the rest mass energy of the pion. Therefore, the energy is m pi c square. Now, this m pi c square will be distributed between muon and neutrino, because your total energy has to be conserved. Therefore, E pi must be equal to E mu plus energy of the neutrino. Therefore, in any interaction which we talk about, the total energy has to be conserved. Similarly, if we talk about the 3 momentum, then the 3 momentum of the initial states, say there are 2 particles in the, again I am taking 2 particles in the initial state and n number of particles in the final state, then the 3 momentum for this will be conserved. And that is why if we take the example of pion, which is decaying at rest, the 3 momentum is 0. This means that P mu plus P nu is equal to 0. And that would imply P mu is minus P nu. That means magnitude of the 3 momentum of muon and neutrino, they are the same. And only the direction is exactly opposite to each other. Therefore, this is neutrino and this is muon. They are going exactly in the opposite direction. Therefore, this is the energy conservation and this is the 3 momentum conservation. Then, if we talk about the charge, then also the charge in the initial, total charge in the initial state must be equal to the total charge in the final state. This is the charge conservation. Then we have the angular momentum conservation, and the total angular momentum of the initial state must be equal to the total angular momentum of the final state. For example, if I talk about a pion, slow absorption of pion in the deuteron, and you have 2 neutrons in the final state, then we have to talk about the angular momentum of the pion. Since this is spin of the pion is 0, and if it is getting absorbed in the S state, and this is the ground state S, that means it is 0. Therefore, orbital angular momentum is 0, spin angular momentum is 0. The total angular momentum for the pion is 0. Then we talk about deuteron. What is a deuteron? Deuteron is a spin 1 system which 96% of the time it stays in the S state. S state means L equal to 0 state. S is equal to 1. Therefore, the total angular momentum for the deuteron is 1. And when we combine this, this should turn out to be equal to 1. Therefore, this will be the initial total angular momentum of the initial state. We are not talking about independent spin angular momentum. We are not talking about independent orbital angular momentum, but we are talking about the total angular momentum, because what we have been taught in basic quantum mechanics, that if Hamiltonian of the system, if it commutes with this, total angular momentum. For example, Hamiltonian for the electron, it does not commute to the orbital angular momentum and spin angular momentum individually. Therefore, the quantum number associated with this J is a conserved quantum number. And that is why, since this is the complete quantum number, in particle physics also, we talk about the total angular momentum J to be the member of exact conservation laws. Then we come to the other two, that is the lepton number conservation and the baryon number conservation. Let me first take a few examples of lepton number conservation, and then I will talk about the baryon number conservation, and then we will see the mixed examples where we can have lepton number as well as baryon number. For example, if I talk about electron plus positron going to electron plus positron, then what we do, we assign electron lepton number. This is +1 for the electron and -1 for the positron. And here also, this is +1 for the electron and -1 for the positron. Now, the important point is why people opted for +1 for the electron and -1 for the positron. It is just convention that the very first particle that we know historically is an electron, and therefore we treat electron, proton, neutron to be among the particles, That is why here also we are treating electron to be particle and assigning electron-lepton number to be +1. But the point is, the field theory demands that the lepton quantum number for positron should be opposite to the lepton number for the electron. Therefore, if you swap it, -1 and +1, that is also equally good. But conventionally, we take this electron to have electron-lepton number +1 and this positron to be electron-lepton number -1. Now, instead of that, if I write E minus plus E plus going to E minus plus mu plus, then what will happen? We are conserving charge, but we are not conserving electron-lepton number as well as muon-lepton number, because electron-lepton number is +1, -1, +1 and 0. Muon-lepton number 0, 0, 0 and -1. Therefore, if you take final minus initial, your Le as well as L mu, they are not conserved. And therefore, this will not be an observed process. Now, similarly, if you talk about a mu decay, a mu minus is decaying into electron plus antineutrino plus muon. Now, here what will happen? The muon-lepton number is +1. This is 0. This is 0. This is +1. And electron-lepton number, this is 0. This is +1. This is -1. And this is 0. Therefore, you see that we will have antineutrino only, because if we talk about charge conservation, then we can delete this guy. We can have a neutrino. But what we'll have? We will have, if we will write here neutrino, then this lepton number will be +1. Therefore, on the right hand side, you have +2 lepton number, and on the left hand side, you have 0 lepton number. Therefore, this will not be an observed process. Therefore, if you can see that a muon is decaying into an electron plus nu E plus nu mu, that is not allowed. But if I write nu E bar, then that is an allowed process, because we are conserving charge, we are conserving electron-lepton number, we are conserving the muon-lepton number. Therefore, when we talk about the leptons, we have to make sure that the conservation of electron-lepton number, muon-lepton number and tauon-lepton number should happen independently. Then if we talk about the baryons, then in the case of baryon, all baryons are assigned, all particles are assigned baryon number +1, or all antiparticles are assigned baryon number -1. Therefore, if you say that I am taking an example, say lambda 0 decaying into P plus pi minus. This pi minus is a pion, this is a boson. Therefore, boson is not a baryon. Its baryon quantum number will be 0. Therefore, what we will write here, baryon number 1 and baryon number +1. Now, that means we cannot write here lambda 0 going to K plus pi minus, because we are seeing that charge is getting conserved, but baryon number is not getting conserved. Therefore, this will not be an allowed process. We have to keep in mind that baryon number has to be conserved. Similarly, if we take a reaction P plus P going to P plus P plus P plus P bar, antiproton, which will have baryon number -1, you see this is +1, +1, going to +1, +1, +1, and -1. Therefore, this will make 0, and you will have +2 on the right-hand side and +2 on the left-hand side. Therefore, you will find that this baryon number is conserved. Therefore, we have to keep in mind that whenever we are talking about baryon numbers, then we have to assign +1 only for the particles and -1 for the antiparticles. For example, if I take the case of lambda 0 decaying into P plus E minus plus, what should be the particle here? Then the answer to that is, first look at the charge. Total charge on the left-hand side is 0. We are conserving charge. Therefore, this particle has to be a neutral particle. Then baryon number is +1 here, +1 here. We cannot afford to have another baryon here. Then we come to the electron-lepton number. This is +1 for the electron. Since on the left-hand side there is no lepton, electron-lepton number is 0. Therefore, this must be a particle which should have electron-lepton number to be -1. This particle should be neutral, as well as this particle must have the electron-lepton number to be -1. And the only option that you have is a nu E bar. Therefore, lambda 0 is decaying into P plus E minus plus nu E bar. This is a process which will be allowed. Again, you cannot have here nu E, because then electron-lepton number will not be conserved. Therefore, we have to keep in mind while discussing the electron-lepton number and baryon, electron-lepton number, muon-lepton number, and tauon-lepton number, as well as the baryon number while discussing the exact conservation laws. Therefore, these are the conservation laws which are we have to obey to see a reaction in nature. Then we talk about the approximate conservation laws. What are the approximate conservation laws? Like 7 exact conservation laws, we have also 7 approximate conservation laws, and these approximate conservation laws are isospin, third component of isospin, third is strangeness, fourth charge conjugation, fifth parity, sixth time reversal, and seventh C and P together. Now you see, when I talk about approximate conservation laws, that means somewhere it will be conserved, somewhere it will not be conserved. And based on these conservation laws, we classify the different processes. Like we know that there are 3 fundamental interactions in nature: a strong interaction, electromagnetic interaction, and weak interaction. Now, if we have been given a process A plus B going to 1 plus 2 plus 3 plus 4 or 1 plus 2 plus 3, then whether that process will get executed by weak interaction or a strong interaction or electromagnetic interaction, those will be decided by these approximate conservation laws. Therefore, what we do, we just say that if we have a strong interaction, we have electromagnetic interaction, and we have weak interaction, then in a strong interaction, all 7 conservation laws, all 7, 1 to 7, they are conserved. they are conserved. All 7 of the approximate conservation laws, they are conserved in strong interaction. While in electromagnetic interaction, the isotopic spin I, we see sometimes in the books you will find bold I or a vector I. This is not a vector in ordinary space, but it is in abstract isotopic spin space. And this was introduced by Heisenberg in 1932 when he spoke about nucleon, where the members are proton and neutron. I will come to that when I will introduce isotopic spin. Let me first talk about in electromagnetic interaction. In electromagnetic interaction, all the letters have become small. Are you able to see it? Hello?
Yeah,
Santin?
I can see it. I can see it. I don't know about the others.
Yeah, but
For me,
I
it's
don't,
fine.
because I don't understand why they have become so small. Okay.
No, we can zoom in and then see. That's not a problem.
Okay. Then when I am talking about electromagnetic interaction, even it is light. Let me just. If we talk about electromagnetic interaction, then I is not conserved in electromagnetic interaction. While I3 and other 5 conservation laws, they are conserved in electromagnetic interaction. While if we talk about weak interaction, in the case of weak interaction, then in weak interactions, all of them, all 7 of them, they get violated. Therefore, this is the way we classify a process into a strong interaction, electromagnetic interaction, and weak interaction processes. And this is an important problem in NET or GET examinations, whether if you have been given in a process and you have to classify it into electromagnetic interaction, weak interaction, and strong interaction, and the criteria is based on isospin, third component of isospin. And even if you look at any process, some of the time directly you can say that this process will be the weak interaction process, or this process will be an electromagnetic interaction process. For example, we know that neutrinos only participate in weak interaction. Neutrinos do not participate in a strong interaction process or electromagnetic interaction process. At the tree level, you cannot think of a neutrino interaction with a photon. Okay. Therefore, if you have an example, for example, n going to p plus e minus nu e bar, or if I am talking about neutrino electron scattering, or if I am talking about lambda 0 decaying into p plus e minus nu e bar, directly you can say that since neutrinos are involved, and from exact conservation laws you are obeying baryon number conservation, lepton number conservation, charge conservation, etc., then this is this is a weak interaction process. Similarly, we know that photon is the quanta of electromagnetic interaction, and we have a process like, we have a process like gamma p going to p plus pi 0. Then in this case, since photon is involved, photon is the quanta of electromagnetic interaction, directly you can say that this process is an electromagnetic interaction process. But in general, we classify them by looking at the I conservation, I3 conservation, etc., to decide whether that is a strong interaction process or electromagnetic interaction process or a weak interaction process. And let me first come to the isospin. Isospin is there for the baryons and the mesons, the particles which participate in strong interactions. Leptons do not participate in a strong interaction. All three generations of leptons, electron family, muon family, tauon family, and their antiparticles, E plus, nu E bar, they do not participate in a strong interaction. Therefore, the important point is that if you see those three generations of leptons, nu E electron, nu mu muon, nu tau tauon, and their antiparticles, for sure that cannot be a strong interaction process, because these guys, they do not participate in a strong interaction. The particles which participate in a strong interaction, they are baryons and mesons, and they together, they are known by the name hadrons. And all those hadrons which we have experimentally observed in nature, whether it is a neutron or proton or lambda or pion or kaon or omega meson, name the meson or name the baryon which you have observed in nature, they are not fundamental particles. These baryons, they are made up of 3 quarks, and the mesons, they are made up of quark anti-quark pair. Therefore, the important point is these hadrons which are found in nature, they have got a structure. They are not point particles. These are all point particles. These are all structureless particles. They don't have any structure. While all hadrons, they have got a structure, they are of finite size, and all baryons are made up of 3 quarks, all mesons are made up of quark anti-quark pair. The antibaryons are made up of anti-quarks, while the antiparticle for pi plus is pi minus. For k plus, the antiparticle is k minus. Therefore, if pi plus, I say that it is made up of u d bar quark, then pi minus is made up of u bar d quark. K plus is made up of us bar quark, then k minus is made up of u bar s quark. Therefore, you have baryons plus mesons. These are called hadrons, and we assign isotopic spin or strangeness to these hadrons. Therefore, we have to keep in mind that when I will talk about leptons, we won't assign isotopic spin or strangeness to those particles. We will assign only isotopic spin or third component of isotopic spin or strangeness to these particles. Okay. Similarly, when we will perhaps if it will be possible in next class someday, we can talk about charge conjugation, parity, time reversal, CP8, etc., where we can see that we have the hadrons. There we talk about these conservation laws. Therefore, when we talk about the baryons and mesons, we assign isotopic spin. And what I am telling you, that this was for the first time introduced by Heisenberg in 1932, because when you switch off the electromagnetic interaction, then, as you know, the mass of this proton is 932 8.2 MeV, while mass of this neutron is 939. The difference is around 1.3 MeV, 939.6 MeV. This is because this difference, or the difference in the mass of pi plus and pi 0, or the difference in mass of k plus and k 0, or the difference in mass of sigma plus and sigma 0, they are there because of the difference in the charges. And if we switch off the electromagnetic interaction, then there is no way to distinguish between a pi plus and a pi 0, or a k plus and a k 0, or a proton and a neutron, etc. Therefore, what Heisenberg said, he stated that protons and neutrons are the two states, protons and neutrons are two states of a single particle. And that state he called it as nucleon, alpha, beta, where alpha is 1, 0. If it is 1, 0, if we are talking about proton, the column matrix is 1, 0. If we are not talking about neutron, then this is 0, 1. Therefore, you have proton and neutron, they are member of isotopic spin doublet. This is what we call by the name iso doublet. Similarly, if we talk about pi plus, pi 0 and pi minus, similarly, sorry. Similarly, if we talk about pi plus, pi 0 and pi minus, then this is an iso triplet. Similarly, rho plus, rho 0 and rho minus, this is an iso triplet. Sigma plus, sigma 0, sigma minus, this is an iso triplet. While doublets are proton, neutron, we will have cascade 0 and cascade minus. We can have k plus, k 0, k 0 bar, k minus. These are all doublets. These are all doublets. And all iso triplets, they are assigned isotopic spin 1. And then the highest charge state will get the maximum projection. This is maximum projection to the highest charge state. For example, proton has got a highest charge. Therefore, if I talk about first pions, pi plus, pi 0, pi minus, then I3 is plus 1 for pi plus, 0 for pi 0, and minus 1 for pi minus. Similarly, this is I3 is plus 1 for sigma plus, 0 for sigma 0, and minus 1 for sigma minus. Therefore, we have to be, this concept is very neat, and we can understand that if it is a doublet, then isotopic spin will be half. Yes, please ask question. Can we just finish this lecture and then we will have questions? Is it all right?
Yeah, fine.
Okay, then we about doublets, then isotopic spin is half for all these doublets, and which will component will get plus half will be assigned to component which has got highest charge state, and minus half will be assigned to the component which has got the least charge. Here also I3 is -1, -1. Here I3 is minus half, minus half, minus half, minus half, and plus half for this. Similarly, if you talk about a delta, delta exists in 4 states: delta plus plus, delta 0, and delta minus. This is quadruplet of states. Therefore, what we do, we assign isotopic spin 3/2 to these 4 particles, and then the highest charge will be +3/2 for delta plus plus and -3/2 to delta minus. Therefore, +3/2, +half, -half, and -3/2. If we talk the antiparticles, now what happens in the case of antiparticles? There is a flip of charge, and since these are the baryons, therefore there will be flip of the baryon number also. Therefore, in that case, if we talk about antineutron, antiproton, then what happens? In the case of antineutron, its charge is 0 and antiproton charge is -1. Therefore, the isotopic spin projection will be +half for antineutron and -half for the antiproton. If we talk about sigmas, then sigma minus bar, sigma 0 bar, sigma plus bar. This is a triplet with baryon number -1. If this is a triplet with baryon number -1, isotopic spin is 1 for all 3 of them. But now this sigma minus bar, the charge has got an opposite sign. This has become +1. Therefore, I3 will be +1 for this, 0 for this, and -1 for this. While we have particles which are only one of their kind, for example, lambda 0 is a particle which is isosinglet. When we call it isosinglet, then that means isotopic spin is 0. Where there are other particles also. Omega 0 is an isosinglet. Eta 0 meson is an isosinglet particle. Therefore, you have isosinglet. These are all hadrons. They have isotopic spin quantum number 0. You have doublets, you have triplets, and you have quadrates. Therefore, this is how you assign isotopic spin to these particles. And based on these isotopic assignment, then you assign the conservation laws. And the conservation laws is simple. And let me just write a general equation, and then I will try to illustrate the meaning of I and I3 conservation. Suppose I am talking about A plus B going to 1 plus 2 plus 3. Like angular momentum conservation, here also, when we talk about A plus B going to 1 plus 2 plus 3, we assign for particle A, isotopic spin IA, for particle B, isotopic spin IB, for this I1, for this I2, and for this I3. This IA and IB, this will have the same algebra as we have the algebra for the angular momentum, and that means values will go from IA minus IB to IA plus IB in the steps of unity. Similarly here, First, we will combine I1 or I2, or you can combine I2, I3, and then we will have I1 minus I2 to I1 plus I2. Let us call those possible values as I dash, I double dash, I triple dash, etc. And then we add I3 to it, and then again we will have I dash minus I3 to I dash plus I3, I double dash minus I3 to I double dash plus I3, and so on. And then we will compare that any one of the values which exist on the left hand side should be there on the right hand side. Then we will say that I is conserved. While when we talk about the projection of the isotopic spin, the projection will always be unique. Whether we talk about proton, that means that will carry a positive sign or that will carry a negative sign. Senthil, I can take 5-6 minutes more.
Yes, sir.
I don't know how much I am able to convince the students, but let me just try. For example, if I say that a lambda 0 is decaying into p plus pi minus. When I talk about a lambda 0 decaying into p plus pi minus, see, all three of them are hadrons because all three of them have got a structure. Then isotopic spin, lambda is an isosinglet, this will be 0. This proton is a isodoublet, and this guy is isotriplet. Therefore, what you see that the total isotopic spin in the final state, 1 minus half to 1 plus half, this can be half or 3 by 2. While here on the left hand side, we have the total isotopic spin in the initial state. This is only 0. Therefore, half, 3 half on the final right hand side and 0 on the left hand side. That means none of these values you are finding on the left hand side. While when you talk about the projection, 0 will have a 0 projection. Proton, half, it will have a projection plus half. And pi minus, this will have a projection minus 1. Projections are algebraically added. Therefore, what will be the sign of this? Minus 1 plus of plus half, and that means minus half. Therefore, I3 is minus half on the right hand side and 0 on the left hand side, such that I3 is not conserved as well as I is not conserved. This is only possible in the case of weak interaction process. Therefore, the example which I have given is a weak interaction process. You can take another example. For example, I am taking the decay of delta plus plus. A delta plus plus is decaying into, say, p plus pi plus. A delta plus plus is decaying into p plus pi plus. What is a delta plus plus? This is the isotopic spin 3 half particle because this was in a quadrate. Therefore, this is 3 by 2. This is half and this is 1. Now, 1 and half can give you half as well as it can give you 3 by 2. Therefore, what you are finding out that one of the values on the right hand side is agreeing to the value on the left hand side. Therefore, you will say that my I is conserved. I is conserved here. While I3, when you talk about, I3 will contain a sign, either plus half or minus half or plus 3 by 2, minus 3 by 2. Since this is a delta plus plus, this is the highest charge state, and therefore its value is plus 3 by 2. On the right hand side, you have plus half, and this pi plus is plus 1. Projections are algebraically added. Therefore, this is plus 3 by 2. Therefore, what you are finding out that plus 3 by 2 is on the right hand side and plus 3 by 2 is on the left hand side. Therefore, you are conserving isotopic spin also. third component of isotopic spin also. Therefore, this will be a strong interaction process. Okay. Similarly, if I take another example, which is interesting, I talk about P plus P going to P plus P plus P plus P bar. There are 4 particles in the final state with antiproton on the extreme right. What will be I? You know, proton, neutron, they were members of doublet. Anti-neutron, anti-proton, they were also member of doublet. And doublets we assign isotopic spin half. Therefore, this will be half, half. On the right hand side, half, half, half and half. This half and half will give you 0 and 1, while this will give you 0 and 1. Then you will combine with the other half. That other half will give you half and then 3 by 2. And then you have this half also. When you have this half, you combine with this half 3 by 2, what you will get? 0, 1 and 2. Therefore, you are seeing that on the right hand side, when you are combining the isotopic spin, the possible isotopic spin states that you are getting, these are 0, 1 and 2, while inside the states you are getting, they are 0 and 1. Fortunately, here 2 of them are agreeing on the left hand side and the right hand side, while in general, even if one agrees with the one of the values on the right hand side, you will say that isotopic spin is conserved. Then this is I, which is getting conserved. What about I3? If you notice, when I will write I3, this I3 plus half, on the right hand side plus half, plus half, plus half, and this anti-proton, remember, anti-neutron will sit at the top and anti-proton will sit at the bottom, and since it is sitting at the bottom, this will have isotopic spin projection minus half. When you algebraically sum them, this is 0, this is plus 1 and this is plus 1 on the left hand side. Therefore, you are conserving I as well as you are conserving I3. Therefore, you are conserving both, and that is an example of a strong interaction process. Is it clear to everyone? Senthil, should I stop here?
Sir, I will ask Joseph to comment.
Huh?
Sir, if you want, you can take some more time, sir.
No, because I don't know about the students, what the students are feeling. I'm not aware of that.
We can also ask them if they want to ask anything in between, then we can pass and then we can continue also.
Okay, thank you. Suppose I write a question that classify this into a weak which one you will say that is allowed and which one is not allowed. If that is allowed, is it a weak interaction process or not? Just I am writing a few examples. Lambda decaying into pi plus, E minus and nu E bar. I am writing K plus decaying into pi plus E minus plus nu E bar. K plus decaying into pi 0 plus mu plus nu mu bar. And finally say K minus decaying into pi minus plus E plus E minus. see here whether this process will be allowed or not. First, the answer is no, because this is a meson, these are the leptons, and this is a baryon. Therefore, baryon number is not getting conserved, and therefore this is not obeying conservation, exact conservation law. In nature, this cannot be an observed process. If you look at this, then K plus is decaying into K plus, the charge is +1. On the right hand side, you notice the charge is 0 because neutrino is a neutral particle. You are not obeying charge conservation. This is not an allowed process. This cannot be observed in nature. You come to the third one, K plus decaying into pi 0 plus mu plus nu mu bar. There is no baryon. Charge you are conserving. But what is not conserved is this muon lepton number. This is -1 for mu plus, as well as this is -1 for nu mu bar. Therefore, -2 on the right hand side and 0 on the left hand side. You talk about the last one, K minus decaying into pi minus E plus E minus. You are conserving electron lepton number. There are no baryons. And you talk about I and I3. Remember, we put K0 bar and K minus in a iso doublet. We put K0 bar and K minus in an isotopic spin doublet. This charge is 0 and this charge is -1. Therefore, I is half, pi minus, this is 1. We don't assign isotopic spin to the leptons. We won't talk about I here. And then I3, K minus, it is -half, pi minus, this is -1. And therefore, what you are seeing that you are not conserving I, you are not conserving I3. Therefore, this is an example of what? This is an example of weak interaction process. This is an example of weak interaction process. Similarly, if I take the reaction, lambda 0 plus P going to K minus plus P plus P. You see, you are conserving baryon number. You are conserving charge, +1 from here and +1 from here. Then you talk about I and I3. Your lambda 0 is an isosinglet. This is 0. Therefore, I3 is 0. This I is half. This is +half. Then on the right hand side, this is half. K minus is -half. This proton is half. This is +half. This proton is half. This is +half. Sorry, let me just. This is +half. Therefore, what you are finding out that this will give you 0, 1. This will combine with half, will give you half and 3/2. While you have half here, you are conserving I, and then 0 and +half, this is giving you +half, and here you are getting +half because you are algebraically adding. Therefore, your I is conserved as well as I3 is conserved. This will be a strong interaction process. Now, just the last example, and then we'll have question and answer session. Pi minus P going to N plus E minus. Now see, when I have written E plus E minus, then for sure, this cannot be a strong interaction process. Either it will be an electromagnetic interaction process or weak interaction process. If I assign I and I3, 1 and -1, half and +half, on this side we have half and this is minus half. You see, I3 is conserved, while you are finding out that even I, when you talk about, I seems to be conserved also, but these are leptons, and leptons do not participate in a strong interaction. Therefore, this is an electromagnetic interaction process. Therefore, this is a tricky question that you are finding out that both I and I3 are being conserved. While what I have told you that in electromagnetic interaction, I3 will be conserved while I will not be conserved. But this is an example, and that is why this can be a net question, that you are finding that I and I3 both are being conserved, but you have to see that you have an electron and a positron, and therefore this will be an electromagnetic interaction process. Let us stop here. If you wish, we can have more discussion later in the next lecture, or whatever we will try to find out, to have more details about the other conservation laws like strangeness and CP and T8, etc. Let's just stop here. Thank you for your attention. Now,
Thank you.
questions.
Thank you, Professor. Yeah. Thank you, Professor.
Thank you. It's my pleasure.
Yeah. So,
So we
yeah,
have
if you
opportunity
have
for
any,
yeah,
yes,
Joseph,
yes.
please.
Yeah, please. So if you have any questions, clarifications to the professor, we can ask. Students, participants.
Yes, please.
Yeah, in the meantime, Joseph, we had one question in the chat box.
Yes,
So
I am
so
reading
the
it,
question,
please.
yeah, okay,
We
yeah.
are assigning some conservation law by assigning BL numbers based on what we observe in nature, and we can predict what reaction will happen and won't. So nature has its own preference in every reaction, like it has own brain and can decide which way the reaction should proceed. So how assigning these conservation laws help us to understand the way the reaction happens, that is how to know what is happening exactly inside the particle for its observed behavior. So what I understand is, if we observe a new reaction, we will modify or add new conservation law to explain our observation. But how these laws can explain the fundamental physical processes and happening inside the particle and in the reaction system. Okay. And then the next question is it possible to create a more abstract theory to explain all the observed reactions and the physical processes inside the particle, which facilitate the reactions inside of having so many conservation laws for different interactions? Let me just try to answer your first question. See, at the basic level, when we are talking about these conservation laws, we have to keep in mind that in a standard model, we have electromagnetic interaction, weak interaction, and strong interaction. Electromagnetic interaction, weak interaction, and strong interaction. And any interaction, you talk, even that is true for gravitational force also, but gravitational interaction is not the member of standard model of particle physics. Therefore, I am not talking about gravitational interaction, but any interaction cannot take place without the help of a mediating quanta. A mediating quanta is a must to have any interaction. For example, if I am rubbing my hands and after some time I am feeling warm, why I am feeling that? Because of electromagnetic interaction. And who is responsible for that? They are the photons. If the cars are flying on the road, or you talk about any chemical reaction, that is an electromagnetic interaction process, what is the fundamental thing that is happening over there is the exchange of a photon. Similar, that means without photons, we cannot think of an interaction. Similarly, in the case of weak interactions, without the help of W minus, W plus, and Z0 bosons, these are known as intermediate vector bosons, we cannot think of any interaction. Similarly, in the case of a strong interaction, without the help of gluons, which are the quanta of strong interactions, we cannot think of an interaction. For example, if I say that electron muon scattering is taking place, electron muon, again you are seeing that you are conserving charge, they are not hadrons, therefore you won't apply isotopic spin. Directly you can say that this is an electromagnetic interaction process, though this can also take place via Z0 exchange, but the probability of that interaction will be very small, as a weak interaction cross section is of the order of 10 power minus 40 centimeter square, where electromagnetic interaction cross section is of the order of 10 power minus 30 centimeter square. Therefore, when we talk about electromagnetic interaction, we generally don't talk about weak interaction. Therefore, what at the Feynman diagram level we say that an electron emits a virtual photon that gets absorbed by a muon. And virtual photon is a neutral particle. This moves in some other direction, and this muon, this absorbs this virtual photon, and this moves in some other direction. Okay, if I talk about a neutron decaying into a proton plus electron plus antineutrino, then this neutron is made up of UDD quark, and this is made up of UD quark. Therefore, what is happening? A D quark is getting converted into a U quark. If you are talking about a conversion of D quark into U quark, that means a conversion of -1/3 charge to +2/3 charge. This can happen only when a D quark emits a W minus and gets converted into a proton. This is a neutron, this is a proton, and this W minus gives E minus and nu E bar. Therefore, at the basic level, it is the quarks which participate in the interaction. If we talk about the hadrons, and for point particles directly you can say, and these quarks are point particles to us, although they are strongly interact among themselves. Therefore, at the basic level, if you are asking the question, then it is the mediating quanta which are responsible for the processes to take place, and that is why I have not talked about the reaction. For example, if I talk about a cascade 0 decaying into P plus pi minus, then a cascade 0 is a straightness -2 particle. This is a straightness 0 particle. This cannot happen because the core configuration of cascade 0 is USS, while this is UUD and this is UD bar. Therefore, you are required to convert two strange quarks to non-strange quarks, and therefore, at the basic level, when you are talking about conversion of two strange quarks, then you require two W diagrams, and then the interaction probability or the cross section will be terribly small. Therefore, the basic level, it is the mediating quanta which plays the important role. And what I have told you, that charge conservation, lepton number conservation, angular momentum conservation, and linear momentum conservation, these are by nature, we cannot violate them at any cost. But some fine bonding, if we observe a process where lepton number is violated, baryon number is violated, or we find that mass of the particle is not the same as the mass of antiparticle, then we have to extend our standard model to the beyond the standard model. The other question is, cosmic rays have high energy, more than we produce in LSC. What would be the future techniques or theory to create those high energy particles? See, recently the particles which have been observed in cosmic rays, we know that they can be of the order of 10 power 20 electron volts, while at the LSC we have achieved tera electron volts of energy, because this is 7 TeV proton collision or lead collision. If we talk about 10 power 12 electron volts and 10 power 20 electron volts, therefore for sure presently it's difficult to achieve that energy. With the present technology, it is almost impossible to get in the next 200 or 500 years to have energy of 10 power 20 electron volts. That is why even people are going for this ice cube experiment or the experiments with the high energy cosmic rays, because you need larger accelerators and bigger areas, and then the technology to handle it. As you know, at LSC, we have the temperature, the vacuum, and all that. They are really with a very high precision. That means that technologically, currently, it is not possible to get the energies that we have obtained in the cosmic rays. Yes, you can unmute yourself and ask question.
Hello, sir. Good evening.
Good evening.
Sir, I have a question like this strong interaction or weak interaction or electromagnetic interaction. These are unitary processes, right? We can model them by unitary operators or unitary processes. So, but unitary processes are reversible and they're deterministic, right? So, why do we have different branching ratios? Suppose a particle can decay into many branches, right? There is
Yes.
no one fixed reaction.
Yes.
But when you talk about this isospin and the projection of isospin, so projection of isospin is like we take the projection of the vector, isospin vector, to different axes or bases. So that might be probabilistic because we make a measurement, and measurement actually collapses the vector, the state of the system. So that is probabilistic. But the interaction by mediating quanta, those should be deterministic, right? Because it's unitary process. So, but why do we have different branches of reactions then? Why do we have different cross sections for different paths? That is my question.
See, the important point is the phase space available for a process. Okay. If you talk about a process, say, for example, A plus B giving you 1 plus 2. Okay. Or it is giving you 3 plus 4, or it is giving you alpha plus beta. Okay. Now, in this case, what I am talking about, anything like that, if I have pi minus plus p going to sigma 0 plus k0, okay, sigma minus plus k plus, okay, or k plus sigma, if I talk about pi plus p, k plus sigma plus, or something like that. Okay, what you see that these particles have got different masses. Okay, their masses are not exactly the same. Sigma 0 mass is different from sigma minus mass. K plus mass is different from K0 mass. Okay, and that means they have got different phase space, the momentum states available in the final states, and that is why, depending upon that, you have the possible reactions and the probability of the different processes to happen. And the more phase space available, the largest will be the probability of finding the particle to decay in that channel. Okay. And that is why when you talk about the cross section, what is cross section? Cross section is nothing but the probability of interaction. Okay. So when we talk about a weak interaction process, where I am telling you that the weak interaction cross section is 10 power minus 40 centimeter square, while electromagnetic interaction cross section is 10 power minus 30 centimeter square. What does that mean? That means that if we have, say, A and B are the two particles, then for that interactions to happen in 1 plus 2, if we have only A and B, only one particle both, then here I have to try it 10 power 30 times to execute the reaction as 1 plus 2 in the final state, while here I have to try it 10 power 40 times to have the interaction in as 3 and 4 in the final state. Therefore, when we talk about the different final states, there are different processes, and those are strong electromagnetic and weak. For example, a strong interaction process, if I'm talking about, that is 10 power minus, the cross section is typically 10 power minus 26 centimeter square or 10 power minus 27 centimeter square. And if I say that A plus B, I have given you the two particles, then that means if I will try 10 power 26 times, then I will have a definite probability of finding out 1 plus 2 in the final state. But for electromagnetic, I will have to try many more times. And for weak interaction process, more than trillions of time, we will have to try more to execute this process. Therefore, the quanta of interaction which is responsible, that is where we have the coupling strengths that come into the picture. This is the place where the propagators comes into the picture at the Feynman level, and these are the points which are subtle and which needs more discussion, that why the cross sections are different, and then for the phase space, for the same interaction, for the same two particles in the initial state, why we have the different branches? This is because of the different phase spaces those are available, and those will depend upon the masses of the particle.
So just a follow-up question for a minute. So by you mean by phase space available, you mean by if we have a larger volume of phase space available, that means more possibilities, right? Because phase space is the specifications of different possibilities, right?
Just let me take the example. For example, if I am talking about E plus E minus going to 2 photons, okay, or I am taking another example. Just allow me to erase it. If I talk about electron proton going to electron proton, and I'm talking about electron proton and a pi 0 in the final state. If I talk about electron proton plus pi plus pi minus in the final state, okay, or see, all of them, all three of them are allowed process. Do you agree with me?
Yes,
all are electromagnetic processes. Okay, all of them are electromagnetic processes. All have been observed in the experiments. Let me tell you also that all these, this is nothing but the what we call in literature as elastic scattering, and these two are what we call by the name inelastic scattering, where you have more particles in the final state, or if the particle changes its nature. Now you see, for the same center of mass energy available to you, say the center of mass energy that is available to you in the initial state is 1 GeV or 500 MeV or 200 MeV, then you see that here you have to create 3 particles first in the final state. Here you have to create 4 particles in the final state. And create 4 particles means first you have to have the rest masses of these particles. First you want the existence of these particles in the final state. Therefore, first you have to consume the energy here 140 MeV, 140 MeV in creating the particle, and then the rest of the energy will be taken as the kinetic energy by these 4 particles. While here, this is simply whatever particles those were there in the initial state, the same particles here, they are in the final state. Therefore, the threshold energy for this reaction is much smaller than the threshold energy for this reaction, and that is why the kinetic energy that is available to this is much larger than the kinetic energy available to these particles. And that is why I am telling you that phase space available to this guy, the third example, will be much smaller than the phase space available to the first guy. Have I answered your question?
Yes, sir. Yes, sir. You have. That's what I said. Like the phase space available means the volume of phase space determines the number of possibilities, the number of branches it can, the probability that the third reaction can take place.
No, this is basically the momentum states available between the momentum interval of P and P plus dP. Generally, we write dqp in 3 dimensions for the particle. But what I am telling you, that you have the energy, you have to first create the particles with the rest masses, and then only the momentum states you can talk about in the final state. So the more, for example, if the particles in the initial state, you have got only 200 MeV of energy. Now, when you have got only 200 MeV of energy, you cannot think of having electron, proton, and 2 pions in the final state. In this case, you have already consumed 135 MeV in creating this particle, because you have to create this particle with a rest mass of 135 MeV. And therefore, if 200 MeV is available to you, then that means kinetic energy that will be divided among this will be very small. And therefore, we will say that from the phase space point of view, this will have a very less phase space in comparison to the first part. Therefore, the probability of the first interaction process will be much larger than the probability of particle electron proton going to electron proton and a pi 0.
Okay, sir. So we can discuss it. Like if you have your email ID, then I can sharpen my question and discuss it later on. Thank
Okay,
you.
okay, fine. Okay. Can I stop here, because I have got another meeting from 8:30. And if you wish, we can have another discussion, another lecture, whatever you like. Thanks a lot.
Thank you, sir. Now I invite Professor Joseph Prabhakar to give the vote of thanks.
Dr. Kamal, are you here?
Yeah.
Yeah, please. So please you propose vote of thanks.
Kamal, sir.
Yeah, I hope everybody will agree that we had a very interesting and illuminating talk by Professor Mohammad Sajjad. So, which is very, very useful, and also students might have got the clarity in how the exact and then conservations, exact and approximate conservation laws works, and also how can we classify the particles based on these conservation laws, and also the kind of reactions, the kind of interactions involved in the reaction. We are very thankful to Professor Mohammad Sajjad. Thank you for this opportunity and then your time, sir. And also, I also like to thank, I also like to thank Dr. Joseph Prabhakar and then Tirusendil and others for organizing this talk. And also, finally, thanks to all for attending this talk. Thank you. Joseph, anything to add?
Thank you. Yeah, thank you very much, Professor. It is really extending session. So you explained very well all the questions, and of course, it's very, very detailed and very simple to follow. Thank you. Thank you very much, Professor.
Oh, thank you very much. My pleasure. Okay, bye-bye.
Thank you, sir. Thank you.
Thank you.
Thank you, sir.
Thank you, Kamal, sir.
Thank you. Thank you.
Prabhu, bye.
Yeah, so we can close the session. We can live
Okay.
disconnected and